Hello, everybody, and welcome to another episode of Evans Imagines. I have forgotten to bring my nice clothes with me on vacation, so you get this version of Evans Imagining Things. So we're going to talk a little bit today, picking up where we left off. This is episode 8. We're mostly going to talk about Einstein and the graviton. We'll start off with the homework from last time, just for those of you who are following along. It looks like there's about 10 or 20 of you who are. So you might enjoy. First, I'd given you the rigid rotor problem from muonium and positronium. So we had talked a little bit about harmonic oscillator, the vibrational aspect of it, when we were talking about the reduced mass. And so I wanted to point out that you have the same relationship here. In the rigid rotor model, you have the, what is it, center of mass or moment of inertia, and that plays the same role as previously we had the center of mass. So reduced mass, sorry. So you have reduced mass in there as well. And so even in the rigid rotor model for rotations, we have the same thing we expect for vibrations. We don't get, we don't get anything special. And so for muonium and positronium, we expect the same sort of inertial mass. We don't expect them to have zero inertial mass. We do expect them to have zero gravitational mass. So they're going to still have rotational states. They're going to still have vibrational states. And those are going to look regular, because those are based on the inertial masses of the things that are the components and their resulting adding togetherness, as you've seen if you just did the problem. So I hope that's clear-ish now that you've looked at the problem. You got into seeing the moment of inertia. I'm going to get it right this time, and where that fits in. Now, relate it to a virtual pair. That's something I didn't bring up when we did this problem, or maybe I did when we did it for vibrations. The point is, if you have a virtual pair, sure, vibrational energy to that pair, rotational energy to that pair, no gravitational energy to that pair. No, I'm sorry, energy. No net gravitational force on anything else outside of the pair, right? Because outside of the pair, net gravity, zero. We have the equal parts. So that's my point about a virtual pair. And I keep making it because, like I say, both Weinberg and Feynman have made that counterpoint to me. And so I think it's very important we spend some time on exactly why that's wrong. Okay, so then the second question I had last time, use symmetry arguments to form the Lagrangian for antimatter, combined with the Lagrangian for matter to form the total Lagrangian. I hope I have not. Okay. Oh, I do have some solutions here. Yeah, okay. So you should just look up the work here of Ulrich. I cited it in the last lecture, but you can Google antimatter Lagrangian, and there's already some work by this guy in Iowa, Ulrich Gensura, I think it is. And it's the answer to this question, but you follow his work all the way through until he introduces the Foldy-Wolfhausen Hamiltonian. At that point, you have to be careful because he's gotten it all right up to that point. He's traced the correct inertial mass in the Dirac equation and everything. But when he starts relating it to a field, this is where I think we have a problem. I think the idea of a field is washing away information. The idea of a field is bringing apart the idea of what's actually causing gravity. Gravity is caused by a thing, not by a field. No field. Okay, so I'm not an Einstein guy. We're going to get more into that soon. I think we have pretty good evidence that wherever general relativity works, it works as an approximation, and it works locally right here. So let's get into it. Oh, and I said pick a question from the list. So the list of things, which I guess we'll just pop right into because that's what I've got here. Oh yeah, and I had a good comment on the homework too. So I'll start screen sharing now. Screen share. I want to share the one with the lecture on it. Okay. So we will now slideshow it. All right, so we talked a little bit about why there's not infinite rotational energy, the same reason there's not infinite vibrational energy, or not a number of vibrational energy. But I'm going to stop giving you homework. So the reason is we're not really building towards a final exam, right? And the questions I'm asking you are getting more and more way out there. The answers are more and more conceptual, trick question type stuff. And you should know, like, we're towards the future now. Like it shouldn't be like you're in class, you're getting hundreds, and all of a sudden you don't know what's out there. That's too steep of a drop off. So I want you to know we're getting close. This is like the cutting edge. We've been talking about it for a while now. I don't know what's out there. I just, I've got my thoughts. And so that's what you're going to hear for the rest of this lecture is my thoughts on antimatter's relative sign of mass, what Einstein said, how Bondi interpreted it, etc. So this is the cutting edge. This is us getting into the spin of graviton versus Bondi-Einstein behavior, theory and experiment. And then we'll get into the rest of this later. Hopefully you've started a little bit of the homework and saw this on there. But 3, 4, 6, we talked about 4 a little bit today. That'll be next time. And then 7, 9, 10 in the next lecture beyond that. So going through the cutting edge, I click the button. Okay. So I thought I had, yeah, it's doing a weird latency thing. What is going on here? Okay. So first we have the Bondi-Einstein negative mass. So I don't like it. I'm going to break down specifically why I don't like it first, and then I'm going to go into the behaviors that I don't like more specifically. So what's happening with the Bondi-Einstein negative mass is the primacy of the field, right? The idea that we have to have this thing that's bending, and if we don't have the thing that's bending the same way for everything, we're not going to have general relativity work or Einstein be right or whatever version of that argument you care about. So the main point I want to draw out is that this theory is crazy. Look at these, look at this. So this is, instead of Newton's laws just being for everything, which is what the graviton theory would be, if you just had Newton's laws with a negative mass in there, you get all of the laws right from that. So instead of that, Bondi has these 4 laws that come from just plugging a negative mass into the field equations. So we're taking these field equations, which have been tested way, way, way less than Newton's laws, and we're going to say, okay, what if they're true? What if we plug a negative m into the field equations? Okay, then you get instead of the typical it bends towards mass, and so everything is attracted to stuff. Now the field bends away, and so everything is repulsed, right? I mean, it's the same argument, and so you wind up with, since everything is repulsed, it repulses itself, it repulses matter, and since matter is this way of a field, it attracts everything. It attracts antimatter. Now, so it attracts something that repulses it. We have a runaway effect. It's very gross. We've talked about that before, though. I think I've dwelled on that at some length. So I think it's pretty important at this point also to notice that the reason we didn't have Bondi thinking this was a big, big problem right away is that he, in the very paper where he wrote these laws, he said, okay, we got to start talking about passive gravitational mass, active gravitational mass, blah, blah, blah. And the reason is because he didn't want to write down these equations as 4 piecewise equations that are very gross. Sorry, there's some work being done on the house and some babies around as well. So I will be occasionally interrupted. Okay, so we have to decide by fiat, and we have to decide a priori, how is the gravitational potential formed? How should opposites behave in that potential? I would prefer a fiat that preserves Newton's laws and the graviton equation. So the here is a explanation of the Bondi-Einstein picture of negative mass. So the you can see antimatter here, of course, is the little shady boys. Matter is the little white ones, and this is the runaway effect. So permanent. People have varying ways of forming this as a problem. An effect, something to be avoided, something to, well, it's just hand wave away. There's many ways to imagine this isn't a problem if you need it to not be a problem. However, I would just like to engage with it as a problem. So also we have negative mass repelling itself. So there can't be negative mass stars. Antimatter is repulsed by antimatter. There cannot be any recombination of antimatter. Cannot get, okay, you can get atoms of antimatter still. And the reason you can get, well, we made these, number 1, so this needs to be rectified. The reason we can get atoms of antimatter and that they have similar characteristics shouldn't quite be the same in this model, but is that the electrostatic or the electromagnetic force is like a much, much stronger than the gravitational force. So even where you have antimatter molecules and you have whatever antimatter nuclei and antimatter electrons, positrons zipping around, you don't have the problem of them repelling each other because they're held together by the electromagnetic effect that is still meant to be attractive. So they're not disproven by the, we have made enough antimatter to tell its vibrational spectrum, as I mentioned a few times now. So this is not directly disproven by that, although actually I think we had 1 part in 10 to the 4th certainty about the vibrational wavelength, or sorry, the vibrational agreement. So we have to look into whether or not that actually, it might rule out this theory, but it's a pretty good idea. So let's go do that paper later. Okay, so here's where the graviton guys disagree. Now, for the moment, me only, but after you've watched this lecture, you too, and some other people. So we only disagree for the negative mass cases. And no, that's not true. We disagree we don't think matter attracts antimatter. We disagree with everything where you have washed away the effect of the two sources interacting with a field, right? And there's information lost in that. So I wanted to make it clear what's like, we think that opposites repel and like charges attract. It's the same thing as regular. It's like adding a negative to electromagnetic force, right? It's like that. Well, let's go double check. Maybe it's just that. So there's a pretty cool proof from Singh. I think I've asked you to look it up a few times now. This is the potential they found. This is generally true for all spin and fields. And it just has these assumptions here. This is the most tight, coolest derivation I've ever seen. So in particular, you can understand it right now, all of you for sure. Look what we got here. We've got a negative to the n+1 times charge times the other charge, two sources. And then we've got e to the minus m r over r. So we're not going to talk about the m's. We're not going to talk about the r's. Lots of other stuff. It's not exactly the same situation. Obviously, electromagnetism, different from gravity. But if we allow electromagnetism as a spin 1 field carrier, and we want a same model, we want a unified model, and we're going to have the graviton be a spin 2, well, the only place n comes into this equation is here right at the beginning. Right at the beginning, it's -1 to the n+1. So you have a negative times electromagnetism. So if you had opposites attract, now you have opposites repel. Bada bing, you're done. Now it's true, Singh does not interpret it that way in his own paper. He wanted it to be accepted. But if you, it's a domain restriction to the considerations of other people that he's doing. Very clear about it actually in the intro. If you read him very carefully, he's saying, well, people only talk about positive charge. But what happens if you plug in a negative to this equation, right? This is an equation that is proven. This is mathematical proof that this is the result of the Klein-Jordan approximation with this sort of pole and residue and spin. So this is an appropriate place to plug in a negative. You don't just, let's plug in a negative, anywhere. You plug it in when it is on the domain of the thing that your approximation works. So if you have an approximation where your domain includes all real numbers, you can just plug in a negative. Here, when you look at his proof, it does. So you can plug in a negative. Please go look up his proof. It's 1988, Singh and Jaganathan. So yeah, as I've mentioned, this is only generally discussed in terms of positive masses, i.e. in terms of a positive and positive E and E prime, because mass charge is what it is in this idea, in this conception, right? Mass is instead the graviton charge of your particle or whatever. So they only discussed in terms of positive masses, but the proof is general and has been studied by Vallata in 2011. So it's not, I'm not the first guy to notice that they actually have this opposites repel behavior. And we have these two cases that are different, right? We have, instead of this case, instead of matter no longer attracts everything, now matter repels antimatter as well, because opposites repel. And the other thing changes from, you no longer have antimatter repelling, you have antimatter attracting. So I thought, apparently I need an extra click animation here. I thought I had that click animation done. Yeah, there it is. Come on. Well, see, there it goes. Now they're attracted. Yeah, see, look at that cute animation. PowerPoint animation is not working really well on this Zoom call. I'm sorry about that, guys. We should stop adding them in there. But we got two cases different. So granted, they're two of the hardest cases to measure on Earth. So it's going to be a while if we don't get the paradigm people to come to us first. And the Bondi people do have a 70-year head start. So it's going to be a little tough for us to beat them. But I think we have the only consistent with field, any field. This is not just quantum field theory. I want to stress that again. This is the result for any field. You cannot have a, I'm gonna dial that back. This is the quantum field theory result only because we have this, we are doing a quantum step when we get into deriving this form of the potential. So I'm dialing it back. There's probably some sort, I mean, obviously it's a field theory, general relativity. So, okay. Oh, all right. But this is a good point. I knew I had a point like lingering around here. My point is that there is no field. This is a proof, right, of all the spin n fields, right? This is a proof. So which n is it that recovers Einstein's behavior? I mean, and by the way, I've called this Einstein's behavior. That's because it's what Bondi did when he plugged in a negative into Einstein's field equations, which by the way might be Hilbert's. But you don't have, you don't really need to sully Einstein with it, right? Because Einstein didn't do that. He just invented the field equations, and he wasn't around anymore for Bondi, so he is not I mean, he was very old, might have overlapped a little, but we don't need to claim this is Einstein's fault. This is Bondi's fault. Bondi made this mistake, and we need to look at whether or not that mistake is possibly consistent with any quantum field theory. Because we know there's a problem here, right? We know quantum field theory and general relativity don't fit together. They're not friends. They don't play nice. And here we found a spot. I think we've got a clue here. We have found a spot where they don't agree fundamentally in the forces that they predict. So I think we have a pretty good spot to figure out whether or not we have their behavior or ours. Now, granted, it's a spot we won't be able to measure for many, many years, but conceptually, it's a pretty important spot. Because they need something besides a field carrier model, right? Like before, we've been pretending that you can have general relativity, you can tack it on with quantum field theory and make the standard model. This says, no, you can't. This says there is no possibility of clasping those together because one of those has one behavior for negative masses and one of those has another. One or the other is true. I would say dark energy and dark matter are the proof, but of which one is which. My resolution is that you should just use the appropriate sign. You know, like you shouldn't do all this Bondi stuff. You shouldn't do all this other stuff. And I'm not the only guy who's doing it out there. There's some really good stuff. The first people who took my ideas seriously here and kept me thinking about it, Bruce Miller at TCU and this group with Manfredi, Chardon, and Rouet. I'm sorry. I know I pronounced those names wrong. I'm sorry to all of you. If you would have a call with me, I could learn how to pronounce your names better. And I apologize. I really appreciate the work you guys have done. This is a really good paper. You guys should all go read this paper, Cosmological Structure Formation with Negative Mass, because in their B, in part B here of antiplasma, that should be called the spin 2 graviton. They are the first people who have appropriately modeled the beginning of the universe. So congratulations, and I give you guys the most respect. Now, granted, it's tough. Like this is a new idea, and you thought antiplasma was what to call it. There was no thinking about what the spin 2 would do, presumably because you thought that would just be the standard model, but it's not. Vallata lets us know that, and I think, yeah. So I think case B should be called the spin 2 graviton, and I think it's looks right. So you can read more about these other cases, Bondi, anti-inertia. They made up a new case because they didn't think any of these cases worked just right. They call it the Dirac-Milne model. It's fine, it works, but I don't like it because it's messy. So I like their paper. I like it a lot. I want to do more with it. I have proposed research with these guys. Please answer your emails, guys. I love you guys. Please, I want to work with you. But particularly, look what's happening in figure 1. Figure 1. They start off with matter and antimatter equally distributed at the beginning of time, and over time, they find antimatter and matter galaxies moving away from each other at higher and higher velocities. That's what's happening, unless I am completely misunderstanding I mean, look at it. You look at it. First, you have them all together in that first frame, 3.7 times 10 to the 7 time steps. I don't care what those are. But you see what's happening in phase space right next to it. Okay, the velocities initially kind of mixed up. Oh, spreading out, spreading out, spreading out. And so if you made an average velocity of each of those little clusters, right? They're forming clusters. It's exactly what we see. So I don't buy that this is not what we see. We see a lot of things that are close together, moving at about the same speed and accelerating away from everything else in the universe that has opposite mass. So I think figure 1 looks really good. I like the antiplasma case. And look at the zoom in. Okay, perfect. This looks just like what we see in galaxies. This looks to me exactly like what I would expect to see. You see a galaxy here, a galaxy here, a galaxy here, and they all formed a cluster. This is exactly what I would expect to see. Exactly what I would expect to see. So I don't understand the conclusions of the paper. I think it's like with all science, right? You have an expectation of what you're going to see, and once you have that expectation, it forms like you can't see the forest for the trees sometimes. So I get that they wanted to see something more like on the right. So they made the Dirac-Milne case. They get this, and they think that this looks like a more reasonable representation of reality. Why? It doesn't even recreate planets moving apart. They don't recreate inflation, I mean, they do in figure 1, but they don't in figure 4. So I don't follow this paper in terms of the logical structure of the results. I do really, 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 really like the calculation. And I think more people should do this calculation. I don't get to the same point. Also, the Dirac-Milne case is just like, it's not Dirac, it's not Bondi, it's not a graviton. It's just like, it's like the Bondi model tacking on an additional assumption. So I didn't like the Bondi model. I don't like the Bondi model tacking on an additional assumption. I like this. I like this first figure 1. First thing you did, you just call it the wrong name. And I mean, in the discussion, they say, blah, 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 this isn't how antiplasmas behave. Yeah, don't call it that. Call it a spin. Call it a graviton. Okay. So this is a pretty short lecture, I guess, because I think this is the end of it. Yeah, so this is just the lecture on me ripping Einstein and Bondi. I have a lecture ready for next time as well, but I'm going to wait until next time because this is vacation and I want to spread these out. But please read ahead, think about it. Remind yourself what the jerk of the universe is, or jolt, what that definition is. Remind yourself how virtual pairs are formed, what a pair means in this context. And yeah, we're going to talk more and more and more about the reduced masses of these things and how that can lead to experiments where we prove that antimatter has negative mass in the sense that I mean it, which is negative mass, negative right here. You plug in a negative and you plug in an E, a charge that is a negative charge. Why is that hard to understand? We have positive and negative charges. I don't understand what positive and negative mass charge, hard to understand. It's hard for me to understand why we are restricting the domain of mass to be positive. I mean, I get it. I've been around. I see. Generally, I am attracted to the things that are near me. But I also have seen people making this assumption where they reason from the things they have seen right here, and then they try to apply that everywhere, and that doesn't work, right? I mean, I guess I have a little bit of a fun shirt on for that sort of thing. But I think we've got to be very careful with when we reason from macroscopic intuition to constraining microscopic states, right? Because macroscopic intuition is fine as far as it goes, but how far does it go? How far away have we ever been relative to where are galaxies, where are galaxy clusters? Always keep that in mind. We have been, I'll do it again, 0.000000005 megaparsecs away, and we are applying what we have learned there everywhere. Hundreds of megaparsecs, 10 to the 11th distance further than we have traveled. We need to be a little bit more cautious applying our local situation to everywhere. That's all I'm saying. Not 100% sure I'm right. I know I'm very confident. Let's put it that way. I will need to see counter evidence better than the alpha experiments. Anybody citing the alpha experiments in the comments, save your breath. They don't show what you think they show. Go look at them again. I would love them to. I want them to be definitive, but they're not. They're very bad experiments in terms of the results we got in 2014 or 13 when they weren't even trying to do that, right? I mean, that was just proof of concept stuff. So yeah, eventually we will potentially get proof that way. We don't have it yet. And it could prove me right. So it might prove them right, it might prove me right. So we have the possibility within those CERN experiments. People are considering the possibility that they're wrong, which is nice, that these experiments could go either way. And I do trust it's an engineering problem. Like, they're going to have the scatter to explain, and it's going to go up or down. So I'll let that be the guide. I would like to make a grand wager with somebody. I am working with a number of people to try to find me somebody high profile who disagrees with me to bet like a bottle of scotch or something. So if you are such a high profile person and you are convinced you are right, email me at bonnie@alum.mit.edu, and we can make a little bet about whether or not antimatter will fall up in these CERN experiments. I want 1 sigma. So I need a little bit more than just, I can't have it be no sigmas, right? Like, the current version of alpha is not enough. 1 sigma is maybe too little, because it could still be, they could still cherry pick a result out, like the 10% result, right, that they want to see. So maybe I should make it 2 or 3 sigma. The reason I made it 1 sigma is they're not going to get 2 or 3 sigmas from this. Not within 10, 20 years, probably, right? I mean, look at how few sigmas they got last time. It's the real point here. They'd have to really ramp up the antimatter pretty far to be able to get confident. So yeah, who knows if we'll be even if we did see antimatter fall up. I should point out again, everybody expects that. Everybody in this negative mass space, even the guys I have told you about today, have antimatter being repulsed by matter. So We're not going to beat the Bondi-Einstein guys this way, but we are going to have some evidence that the standard model is wrong and we need to move on. Thus, I'm pointing out we have some experiments suggesting our way is the highway, and that you guys should all get on board and do some calculations. Do I have any relevant papers to this? Let's see. Spin 2 graviton versus Bondi. I haven't really, it's kind of like a review level paper I need to do here, but so far, I don't think there's a specific paper that mentions this. I do call it out in a number of papers. Go check out my ResearchGate if you'd like to read more. But for now, yeah, you know what? Let me stop the screen share so I can pop in with a little bit more yammering here at the end of what I presume is one of our shortest meetings ever, since I didn't double check how long this deck was before I started. But yeah, I've enjoyed talking to you guys again. Thank you for exit full screen. Yeah, for watching Evans Imagines. I like and subscribe. You know, if you're watching the 8th lecture, I'm assuming you've done that by now. And yeah, get ready for next time. Like I said, we're going to talk about reduced masses, virtual pairs, negative jerk, man, maybe some other stuff if I want to, because this wound up being pretty short. All right, guys, see you next time.